Welcome to the new project. Imagine playing rock, paper, scissors with a computer and watching it instantly understand your hand gesture, just like a human would. What feels like a simple game is actually a surprisingly difficult problem for machines, because hands move quickly, change shape, and look very different depending on lighting and angle. In this project, we build the rock, paper, scissors detection system, an AI-powered computer vision model that can look at images or videos and accurately recognize whether a hand is showing rock, paper, or scissors. Instead of relying on rigid rules or manual feature extraction, the model learns directly from real images and figures out the patterns on its own. The challenge here is teaching a computer to see and classify hand gestures reliably in real-world conditions, where backgrounds are messy and gestures aren't always perfect. By the end of this project, you'll see how computer vision and supervised learning come together to transform a fun idea into a practical and impressive AI system. Now let's get started. Now let's zoom in on what we're actually going to work on. In this project, rock, paper, scissors detection, we're going to build a computer vision system that can look at an image or a video and understand which hand gesture is being shown, rock, paper, or scissors, just like a human would. The goal is simple and beginner-friendly. We'll take visual input such as a photo or a video frame and let our program automatically detect the hand, draw a box around it, and label it with the correct gesture. Instead of writing complicated rules ourselves, we'll use a trained AI model that learns patterns from real images and makes predictions for us. Along the way, you'll practice core Python skills that are essential for real projects. You'll work with Python libraries, load and manage files and folders, run functions, and handle model outputs. You'll also see how Python is used to connect different tools together, such as a deep learning model, image processing, and visualization to create a complete working application. By the end of this project, you won't just understand how object detection works. You'll have a practical example that shows how Python and computer vision can turn an everyday idea into something interactive and intelligent. This is a great step forward if you're learning how AI projects are built in the real world. In the next step, we'll walk through the project flow one piece at a time, starting with a clear step-by-step example so you can see exactly how everything fits together. Before we can train or run our yoga pose prediction model, we need to prepare our working environment. First, we install Ultralytics, which provides YOLO v8. This library gives us access to a powerful pre-trained pose estimation model, so we don't need to build everything from scratch. Next, we import the libraries that we'll use throughout the project. We import YOLO from Ultralytics to load, train, and run the pose estimation model. We import Matplotlib to visualize images and prediction results. The OS and Glob libraries help us manage files and folders in our dataset. We also import tools from IPython Display so we can show images and videos directly inside the notebook. Since this project runs in Google Colab, we import files to upload our own images and videos for testing. OpenCV is used for image processing tasks such as color conversion. The Base64 library allows us to display video output smoothly, and MoviePy helps us convert and play the prediction videos generated by YOLO. With all the required libraries installed and imported, our environment is ready. Now we can move on to the next step and start working with the data. Now let's move on to the data collection step where everything really starts to come together. For this project, we use a ready-made rock, paper, scissors dataset from RoboFlow, which contains images of hand gestures that have already been labeled with bounding boxes for rock, paper, and scissors. We begin by exploring the dataset in the RoboFlow universe to understand what the images look like and how the gestures are represented. This helps us confirm that the data matches our goal and that each class is clearly defined. Once we're happy with the dataset, we download it directly into Google Colab using RoboFlow's Python API, which saves time and avoids manual file handling. After the download, the dataset is automatically organized into training, validation, and test folders, and a data YAML file is generated for us. This file tells YOLO where the images are located and what class labels to use, so we don't need to configure everything by hand. With the data in place and properly structured, we're now ready to teach the model how to recognize each gesture. In the next step, we'll move on to training and start building the object detection model using this data set. Now we're at the most exciting part of the project, training the model. This is where we take everything we prepared, the dataset, the labels, and our YOLO setup, and actually teach the model how to recognize rock, paper, and scissors from images. We start by loading a pre-trained YOLO 8 model. That's important because we're not training from scratch. The model already understands general visual patterns from a large dataset, and we're fine-tuning it so it becomes very good at our specific task, detecting hand gestures. This makes training faster and usually improves accuracy, especially when the dataset isn't massive. Next, we point YOLO to our dataset using the data.yaml file. That file is basically the roadmap for training. It tells the model where the training, validation, and test images live, and it also defines the class names. Once that's set, YOLO can automatically lead the data and start learning without us manually loading images one by one. Then we run the training process by choosing a few key settings, like how many epochs to train for, the image size, and the batch size. As training runs, YOLO prints out progress logs for each epoch. These logs show the training losses and evaluation metrics updating over time, so we can see whether the model is improving as it learns. The goal is to see losses gradually go down and performance metrics like MAP, precision, and recall get stronger. Once training finishes, we'll have a trained model that can detect and classify the gestures with confidence. In the next step, we'll look at the training history so we can clearly visualize how the model improved over time.